So far in this module, we've gone over how to identify a buffer and how to identify a solution that meets the requirements for a buffer. In this video, I'm going to be going over how to create a buffer solution using a titration. So if we have a beaker and we have a solution of just water and we add 1 molar of HA, which we will call a weak acid. In the video I made that went through each individual beaker to decide whether we had a buffer solution, we would call this beaker not a buffer, simply because this beaker is missing the conjugate base to the weak acid HA. So in order for this beaker to satisfy the requirements of a buffer, we would need A minus, which is the conjugate base of HA, in order to say that this is a buffer. Now, there is a way to create a buffer using this beaker using the method of titrations. So what we will do is we will add a titrant to this beaker, meaning we will add something from the outside of this beaker into this beaker that can create a buffer. Now, if we look at our current beaker, the only thing we are missing from this beaker is the conjugate base. So in order to create the conjugate base, we need to remove this hydrogen. So it makes sense that if we were to add a titrant to this beaker, in other words, run a titration, it makes sense that we should add a base to this beaker that can take the hydrogen from HA and make A minus that can create a buffer. So it turns out when you do a titration, you are either adding a strong base or a strong acid to a beaker. Now, when do we see a titration with a strong base versus a strong acid? Well, if we had a scenario where we have 1 molar of HA, which is our weak acid, we should add a strong base to take away the hydrogen to make a conjugate base. Now, if we had a beaker filled with water, and we had 1 molar of A minus, which is a base, we should add a titrant to this beaker that can give A minus a hydrogen so that we can make HA, which will be its conjugate acid. That can make a buffer. So in this case, we should use a strong acid. In the case above, we should use a strong base. So if you have a weak acid, you should use a strong base as your titrant to run your titration. And if you have a weak base, like we have below, we can add a strong acid, and note that this is a strong base and a strong acid, not a weak base and weak acid. And what this can do, so in the case above, if we add a strong base, what this will do, it will take away that hydrogen, and we'll be left with A minus. And below, what we can do is we can add a hydrogen, and this will be HA, and we will have now a certain amount of a weak acid in its conjugate or a weak base in its conjugate. So now I want to continue by going into how we can run a reaction with a weak acid or base with a titrant to then create a buffer solution. So if we have a beaker and we have H2O, and there is 1 molar of CH3COOH aqueous. And this is a weak acid. Now, before, we simply called this not a buffer because it is missing its conjugate base. So if we were to remove this hydrogen we would be left with CH3COO minus, which would be its conjugate base. And then we could see if this beaker could meet the requirements of a buffer. So what can we do to create a buffer? Well, we can run a titration where we can add, write it right here, we can add a strong base. So if we add a strong base, we can then remove the hydrogen from CH3COOH, and we can make some conjugate base to give ourselves a chance, I should say, to create a buffer. So let's say we add 0.5 molar of a strong base. Now, the most common strong base you will see in a titration is OH minus, which is hydroxide. So let's draw our new beaker. There is water. There is 1 molar of CH3COOH aqueous, and there is 0.5 molar of OH minus aqueous. So at this point, when you are solving a titration problem, you need to draw a beaker with what you have and what you have added. And then what you want to do is to draw an ice table to see the reaction that will proceed. So what I'm going to do is draw an ice table for our new beaker. So our acid is CH3COOH aqueous. Now, in previous reactions, we have reacted CH3COOH with water. However, we need to note that water, whether it's acting as a base or an acid in a Ka or Kb type expression, is weak. So when we add a strong acid or base in a titration, you want to react your original species with the strong acid or base, because a strong acid or base takes precedent over our weak H2O. So what will happen here is we will react OH minus. It is the strongest base in our beaker, so it wants to react with that acid more than water does. So the products of this reaction will be water, because OH minus will take a hydrogen from CH3COOH and become H2O, and this will be CH3COO minus aqueous. So what we have to do now is we have to fill in our ice table. So for CH3COOH, we started with 1 molar. For OH minus, we had 0.5 molar. And for H2O, we do not include it in our ice table because it is a liquid, so we would not express it in an equilibrium type expression. So CH3COO minus, we do not have any at the beginning. Now, it is important to note, in our ice table, we can now see some conjugate base forming, which is really good because we are trying to create a buffer, which means we need a weak acid or base and its conjugate. So it's important to note that as you're doing a titration problem, you should be forming the conjugate to whatever you had at the beginning of the reaction. So we can say at the beginning there was 0 molar. So what is going to happen? Well, in a weak acid reacting with water, we have to do minus X and minus X because we do not know how much of the acid is going to react because it is weak and water is weak. So we need to set up a Ka expression. However, it is extremely important to note that when you are doing a titration, and the first step to any titration is to add a strong acid or base, that means in this reaction, we are working with a strong species. OH minus is a strong base, so it doesn't matter that CH3COOH is weak. OH minus is a strong base, so it is going to take the hydrogen from CH3COOH 100% yield. So what we can see is there is 0.5 molar of OH minus and 1 molar of CH3COH. So simply, the species with less, which in this case is OH minus, there's 0.5 and there's 1, this is all going to go away. It is 100% yield going to react. So we have 0 molar left, right? It all got used up because it is a strong base. It wants to grab as many hydrogens as it can. So there's 0.5 molar available to grab hydrogens, and it's all going to get used up. So this is minus 0.5. CH3COOH was willing to give as many as OH minus was willing to accept. So CH3COOH, it can't give away all 1 because there wasn't 1 molar of OH minus to accept hydrogens. So it will give away as much as there is OH minus to accept. So we'll be left with 0.5 molar. So what happened on the product side? Well, we don't care about water, but we started with 0 of CH3COO minus. Now, what happened here? CH3COOH reacted with OH minus and gave it a hydrogen. So in the meanwhile, there are CH3COO minus molecules starting to form as this reaction runs. So this will be plus 0.5, right? Because every time we run this reaction, we are going to take CH3COOH, react it with OH minus, give it a hydrogen to create H2O and our conjugate base. So 0 plus 0.5 is 0.5 molar. Now note, this is much different from an ice table when you are reacting a weak acid in water or a weak base in water. This is simply using a strong base to take a hydrogen from a weak acid. So in reality, we don't really need to draw out an ice table with an equilibrium expression for Ka or Kb. We simply know that as much base as we have is going to react. So we have our equilibrium concentrations for this reaction. Now, what you're going to do is to draw your leftover beaker after the reaction is run and see, do we have a buffer? So now we have water still, and we have 0.5 molar of CH3COOH, and we have 0.5 molar of its conjugate base. Note, we used up all of our strong base. And remember, in order for it to be a buffer, you cannot have any strong acids or bases in your beaker when you run your titration. So you can add a strong acid or base as a titrant to create a buffer, but when you draw your final beaker, there should be nothing strong in your beaker left. So it works out that we have CH3COOH and 0.5 molar of CH3COO minus. Let's check to see if this is a buffer. Well, CH3COOH is a weak acid, and we have its conjugate. That works out, and the Ka will fall within that range for a weak acid. Then we need to check the ratio of our acid and base. So the ratio of base to acid is going to be 0.5 to 0.5, which will equal 1. And as long as that value falls between 0.1 and 10, that checks out. So our requirement number 2 works. And requirement number 3 is simply that we need the concentration of our acid and base to be between, I should say, 1 times 10 to the negative 3 molar and 1 molar, which these both do. So it is really important to be able to go through a titration problem and draw the beakers and the ice table to get your final beaker to see if you have successfully created a buffer. So one last thing, it is important not to just look at your original beaker and say, this is not a buffer. We need to see, can we add something strong to create our final buffer?